before we design specific search algorithms, we need criteria to compare them. We usually measure performance in 4 ways. The first one is completeness. Will the algorithm always find a solution if one exists? The second one I prefer in that order is optimality. If it finds a solution, is it the best one? Example, let's say shortest path or least cost path, things like that. The third one in the order should be the time complexity. How long does it take to find a solution? And the fourth one should be the space complexity. How much memory does it use in the process of finding the solution? Now for time and space, we measure difficulty in terms of the state space. Like in computer science, this is mod V plus mod E, like the number of vertices, which are states, plus the edges, which are links. In AI, however, the state space is often implicit, okay, generated by rules, not stored fully in memory. Like when you expand a node, you generate some states. So this is depending on what kind of rules you are using. And you don't want to store fully in memory and can even be infinite, okay? So depending on whether you are storing all of them in memory or not, or you can store them in memory or not, can be infinite at times. So instead of defining the state space in that way, we define in a different way. We describe complexity in terms of 3 quantities. The first one is now, B, which is the branching factor, which is nothing but the maximum number of successor per node. Like in this graph, in this tree I have drawn, like the root node and these are the child. So every node is like having 2 children, like it's a binary tree, okay? So the branching factor is 2, maximum number of successor per node. D is the depth of the shallowest goal node, okay? D is the depth of the shallowest goal node. That means, let's say, a goal is, let me move over here and see if I can draw. Let's say this is a goal node and this is a goal node also, G. So then you can have multiple goals in a problem, okay? Like let's say you are doing checkmate in chess, okay? So you can do checkmate in different way, but the ultimate goal is to checkmate your opponent, but there are many different paths you can take to go to the checkmate state. So let's say this is one of the checkmate state and this is one of the checkmate state. This is different than what you will do in the Romania map problem. There is only one destination, which is Bucharest, but here there can be 2 goal nodes. Let's say Sudoku, you solve a Sudoku, but you can fill different numbers in different spaces and still can get the same result. So you can have multiple goal nodes. This is important to understand. So the shallowest goal node, the depth of the shallowest goal node, that means from the root, is this one. So this will be the depth, okay, D. And then M is the maximum length of any path in the state space. Let's say this is the maximum length of the path, okay? This is M basically. This is M, okay? So sometime in the tree we also call it a height, and this is B, number of children at every level you are creating. So it's a B. So you see there are B number of nodes at this layer. There will be B and B. That means B square number of nodes at the second layer. That means at the 0th height, this is b to the power 0, which is 1. Okay, b to the power 0. That the second level, the first layer, it will be b to the power 1. That means b number of children. At the third level, which you identify at 2, you will have b to the power 2, which is 4 children, right? So in that way, if there is a tree of height m, so then you will have how many? You will have b to the power m number of children. And then you can add them up to find how many total number of children are in this tree. And if you need to store all the states, then you have to store all these nodes together. Okay, so this is the explanation of how it works. So time complexity is often measured as the number of nodes generated, and space complexity as the maximum number of nodes stored. So as I said, if you need to store all this node, you have to add them all up and find out how many total nodes are there. So finally, when judging a search, we think about costs. Okay, so that there are basically two types of cost. One is the search cost, that means the resources, the time and memory used for the search algorithm. Okay, another thing is the solution cost. That means for the for this problem, Romania map, let's say Arad to Sibiu to Râmnicu, Vilsia, Pitești, Bucharest, what is the path, the total cost of this path? So this is called the solution cost, which is the path cost of the solution itself. So two types of cost. One is the actual cost for the solution, and the second thing is the search cost. That means how much memory and time the algorithm is actually using. So the total cost will be the search cost plus the path cost. Okay, so as I said, the example in the Romania map, the search cost is the time the algorithm spends exploring, while the solution cost is the kilometers of the final route. Sometimes we may accept a slightly longer path if it saves a lot of search time. Okay, this is a trade-off between thinking and acting. So after this, we will discuss about multiple uninformed search strategies. So which basically why we call uninformed. So because the algorithm has no extra knowledge beyond the problem definition. It only knows how to generate the successors and how to recognize a goal state. That's all. The main difference between search strategies is the order in which they expand the nodes. Okay, if a strategy has some idea of which states are better or more promising, we call it an informed search or heuristic search. I mean, if the algorithm knows that, okay, I should choose this state to expand instead of that state, then that means they have an informed vision, or they know what to do or how to be better or more promising than other algorithms. So, and they are called informed search. But in this chapter or in this section, in the next video, we'll discuss only the uninformed search algorithm, which are breadth first search, uniform cost search, depth first search, depth limited search, and iterative depending search.